Okay, so back into 13.2 here, we're talking about vector valued functions. At the end of class last time, I just briefly mentioned a little bit about limits, right? And so let's just formalize all of that stuff here. We'll need that in the next section when we start talking about derivatives and integrals of vector valued functions. Let me just say this. So without giving the formal definition, so you can spend the time writing out what it means to be a limit of a vector valued function. Maybe just write it like this. RT equals the limit. T goes to A. So again, I'm assuming here I got my vector valued function looks like this. Right, so this in terms of there, if you just think about what the distance means in three-dimensional space, right? The only way, so again, what does it mean for the limit to equal some vector? So that'll correspond to some point in space, right? And so for the limit to approach that, it just means your point, the tip of your vector, right here, is getting closer and closer to that point in space, right? And the only way to get close to a point is for your x values to get close to the x values, your y values to get close to y values, and your z values to get close to them, right? If any one of those is off, everything's going to fall apart. And so you can spend a lot of time doing the formal definition, and in more of an advanced calculus class you might. But for our purposes, I hope that you can believe the idea is that as long as this limit slides in, that's what you get. And the only way it's going to exist is that all of these guys exist. Does that make sense?
So we will get a vectors at the end.
Right, so you'll get a vector at the end.
So what if they represent that instead of I, J, and K, is that we just get an equation?
Right, so if this is, Fi plus Fj plus Fk, or Hk, sorry. Right, your limit is just the limit as t goes to a of f of t times I plus the limit as t goes to a g of t. These are just numbers times j, but again, they'll just correspond with that same thing. So that notation, it's...
So I don't need to transfer this the equation into the vector. Do I need to?
Well, it is a vector, right? This is a vector. It's something times a plus something times j plus something times k. That's a vector. It's just another way to write this.
Okay.
So, and then, all right, is that okay? So I think, well, let's just do one example. So I'll take the limit as t goes to 0 of the vector valued function e to the t minus 1 over 2t, comma, doesn't really matter, I'm just making stuff up here anyway. Okay, so all you do is take those limits term by term, right? And again, if you see these, you don't have to write this line out, but I'm just gonna go ahead and write this one. And I should mention too, here, I'm talking about the limit as t approaches a. This a could be infinity or negative infinity. Those are allowed as well. You still just do the same thing, right? Take it in each part. Okay. So if you know the answer, that's fine, but let's not, what's this first one behaving like? What's the form of it? I'll write it like this. It's a 0 over 0, right? If I plug in 0, and so how can we compute that limit?
L'Hopital's.
L'Hopital's rule, and again, you might know it. If not, I'm just gonna skip that middle one. The middle one, we can just do what?
Just put in.
You can plug in t, there's no problem, right? As long as the thing's well-defined, everything's good. Sine is continuous is essentially what it comes down to. So if you apply L'Hopital's rule on this first one, what do you get? E to the t over 2, right? And then this one, we can just plug in the 0, so we end up with sine of 1, right? How about the next one?
One. Minus one,
Minus
also
one.
minus one.
Okay, where'd you come up with that?
2 square root minus 1 equals 2 plus
Okay.
1.
So you're just plugging in on this one as well, right? So negative 1 over 1. So 1, not negative, I thought I heard negative 1, so I was confused. But just 1, right? Question?
What if I just make t squared minus 1 equals to t plus 1 times t minus 1?
Like that.
Oh, that is
And then the t
positive
minus 1's
and-
cancel, so then the positive 1 ends up, right?
Yep.
So that's fine, and you need to do that if you were approaching 1 instead of 0, right? Then we would have wanted to have done that. But in this case, we end up with what? 1/2 sine of 1 and 1, right? Okay. All right, continuity. So let's think back to, you don't have to write this down, but all right, so when we talk about a function being continuous, what was the idea? What did it mean for a function to be continuous? In terms of drawing it, you remember? So let me just draw a couple things. Is that a continuous function? No, it's got that jump in it, right? What about if I just do this? Is that continuous? No, it's got a hole in it. What if I do that? Is that continuous? No. So what was the definition? So the one thing we talked about was that you could draw a continuous function without lifting your pen or pencil, right? Or chalk. But in terms of the limit, what was it? That the limit as x approaches a of f of x equals f of a, right? You actually get the value that you expect when you get there. So with this second example I drew, right, something like this would be defined at A, right, as whatever the dot is, but it wouldn't be continuous because you wouldn't be the same, you wouldn't be getting the same value as your limit, right? So, definition for continuity of a vector value function is exactly the same. So, vector valued function is continuous at t equals a if and only if r of, oh, sorry, I'll write it this way. So now we have the definition of what it means to take the limit, right? And so you should get continuity if you just get the same thing. And it shouldn't be too difficult to see, but a vector valued function is going to be continuous. Well, let me put it this way. It's at least going to be continuous everywhere the component functions are continuous, right? If all of the components of the vector valued function are continuous, well, how do we compute the limits? We do it component-wise. And so if each piece is continuous, then your whole thing will be continuous. Okay? And so that's really all you need to take away. Yeah, I don't think I want to say anything more. Let's stop there.